All right, guys, today we're going to look at the second PowerPoint in the history of atomic theory. Okay, so hopefully we can get through that. Remember, you don't have to watch all these all at once. You can chunk them, you can break them apart. Remember, you've got, basically 7 days in the week there to get things done. So take notes as you go. Email me if you have questions, and we will move right along. All right, so let's jump in to Atomic History 2. Okay. Now we're going to do a little overview from the last PowerPoint. We're also, or last lecture video, covering the last PowerPoint just real quick, and then we're going to keep moving. This slide, or this video is shorter because we only have about 17, 18 slides. So hopefully it won't be quite as long. All right. So from the other video, we talked about these major achievements here in science. I kind of put it all into one slide for you. Make sure you know these folks, right? Especially who discovered the electron, who discovered the nucleus, and we give him credit for the proton, right? Make sure you know, we use the wave model today. Make sure you know that Chadwick discovered the neutron, right? Okay, so just as a review, in case you need it, there it is all at once. So models are up top. Here are the models. Okay, here are the names. You do not need to memorize the years, but it is helpful if you know what order the men go in there, these 4 guys. So Dalton, Thomson, Rutherford, Bohr. Okay, so a couple other things we're going to discuss. Okay, some new scientists that are important. Number 1, Dmitry Mendeleev. All right, he organized the periodic table by increasing atomic mass. Dmitry Mendeleev is super important. He is who we give credit to coming up with the periodic table. We don't give him that credit because he was the first person to put the elements into a table. Lots of scientists had done that. We give him credit for it because he recognized that by putting them in the correct order, that you could predict things about elements that hadn't been discovered yet based on where they should appear in the periodic table. So if you think about the modern periodic table, looks something like this. When Dmitry was doing his research, some things that we had discovered were boron and aluminum, which are these 2 elements right here. But gallium had not been discovered yet. Gallium. And gallium was unknown. And when he was, they had the elements on like little cards. They called them tiles. It's actually what we call them today. So like, let me grab my periodic table here. Stuff on this. So each one of these is called a tile. And so boron is discovered. Aluminum was discovered. Zinc was discovered. But germanium had been discovered. And a lot of people just put germanium right there, right after zinc. It was the next heaviest element. But what Dmitry did was he left a hole, a spot where gallium was. And he called it Eka aluminum. He said it'd be underneath aluminum. And he started predicting things about the properties of gallium, even though it had never been discovered yet. Later, gallium was discovered, and it turns out a lot of his predictions were right, and so he gets the credit. The issue with his periodic table is that it was done by mass. Okay, we'll talk about Henry Mosley on the next slide and who fixed that problem. But some other people we did mention, Max Planck before. He discovered the quantum nature of energy, okay, the fact that energy is given in discrete packets. So even though light moves as a wave, it acts like a particle as it moves, okay? So each one of those little particles is like a packet of energy, and that would be like a photon or an electron. They both do that, okay? Robert Millikan, we talked about as far as the oil drop experiment. Henry Mosley, he's new, just like Mendeleev. He fixed Mendeleev's periodic table by using the atomic number. And the atomic number is simple. The atomic number is the number of protons in the nucleus. So if I want to draw hydrogen, hydrogen is atomic number 1. I know that hydrogen has 1 proton in the nucleus, and it has 1 electron going in the first orbital. Okay, this the S-shaped orbital. that was a big deal. Louis de Broglie, we talked about, did the wave mechanics and the fact that electrons move as both particles and waves and the dual nature of particles. Werner Heisenberg did the Heisenberg uncertainty principle. All right, now, we talked about these orbitals and
all-stars, attention, we will be starting in about 5 minutes.
Announcement here at the school. Sorry about that. All right. Anyway, these are the orbitals. These are the shapes of the orbitals. Okay, so over here, the first 2 rows, 1s and 2s, or sorry, the first 2 groups, 1 and 2, both have s orbitals, s for sphere, right, because the orbital is a sphere, and at the middle of this is the nucleus. All right, so that little teeny tiny red dot right there is the nucleus. Right up here, so you know where I'm drawing. That's the nucleus. Now, in the second orbital, this blue dot right there, that's that orbital. And here, the white dot is that orbital. And so they're nested, all right? The orbitals are nested inside one another. They get bigger and bigger and bigger and bigger, okay? And so the further you get from the nucleus of the atom, the more energy the electrons have, the more space they move around in. Now, if you look over here at the d orbital, these are, so this is called the s. This one here in blue is the s orbital. The d block, the middle transition elements, these are called the d block orbitals, or actually, sorry, just d orbitals. They're on the d block, the periodic table. D orbitals. All right. These are the p orbitals. And these are the f orbitals. So if we draw a periodic table, the first 2 groups are the s orbital. There's the d block. Here is the p block. Something to keep in mind, helium is part of the s block. It goes right there in that spot. So helium is actually part of the s block. And then down at the bottom, you have the f block orbitals. Okay, this is what they look like. We'll talk more about them as we keep learning. Now, some things that we can do with our knowledge of the periodic table. Okay, first we can figure out how big an atom is, its radius, right? We want to know how large the atom is from the center of the nucleus to the outermost electrons. Now, this is hard because you can't measure an atom directly. They're too small, especially the smaller atoms like hydrogen or helium or lithium, something like that. So what we do is we get 2 of them, okay, and we put them next to each other, and we measure the distance from the middles and cut that in half, and that tells us the atomic radius. We usually measure that in picometers, which is 1/1,000,000th of a meter. So this would be an example of how you would measure the distance between 2 hydrogen atoms. You get them together, you measure the distance right from here to there. That's our overall distance. Obviously, in the middle, right, 1/2 times distance would equal the atomic radius. Looks like we're going to get another announcement. I don't know if you guys can hear that. I'm sure you know. Hold on just a second. All right, sorry, I'm back. They were playing music over the announcements for some reason. Okay, so that's just a quick review of the other stuff and a little bit about atomic radius, just so when we're talking about the size of the elements, you know what we're talking about. Let's talk about some new stuff, all right? Isotopes, atomic numbers, mass numbers, all that good stuff. Now, we did talk about this briefly when we talked about Dalton, right? We talked about the word isotope because it said that Dalton's precepts about all atoms being the same wasn't accurate. So we want to kind of get into that, right? And that's going to take us into a discussion about atomic number, mass number, isotopes, all of it and how they go together. Something to keep in mind, you're going to see this word nuclide, all right? This is, you can think of it in like a single atom, okay? Or a nuclear unit, all right? And in this case, nuclear is referring to the nucleus, not necessarily like a nuclear reaction. So what's an atom made of? Well, it is comprised of subatomic particles. Now, for some reason, people struggle with this. Sub means smaller or below, smaller than the atom particles. So a proton is smaller than the atom that it's a part of. Like, that should make sense. But a lot of times people struggle with that. I'm going to switch my pen color here since I have a lot of red on this page. Let's go with green. Protons have a charge of 1, and they have a mass of 1 atomic mass unit. And this is their symbol. Okay, right there. We've talked about that quite a bit. The neutron has no charge. It's neutral, has a mass of about 1 AMU. Protons and neutrons weigh about the same. Okay, there's its symbol. Electrons are negative. Symbol is E minus. It has no significant mass, which means if we're trying to figure out how something weighs, we leave it out. Now, you might think, well, we want to be really accurate. We want to account for the mass. Well, let me give you kind of an idea of what an electron weighs. It takes 1,800 and I think 64 electrons, something like that, to equal 1 proton. So as small as a proton is, an electron is almost 2,000 times smaller. So we're really not worried about them in terms of mass. Elements, anytime you say the word element, you are implying that it is a neutral atom because elements always have the same number of protons and electrons. It's a definition kind of thing. The atomic number, which this symbol for atomic number is Z, all right, is the number of protons in the atom. So if you see, Z equals 2, well, that's helium, because helium is atomic number 2, okay? If you were to see, Z equals, I think 45, yeah. Z equals 45, well, then we must be talking about rhodium, which is an excellent element, right? Because it's number 45. So the atomic number is Z, all right? When Z is equal to 2, we're talking about helium. If Z is equal to 45, we're talking about rhodium. If Z is equal to whatever, that's the atomic number of the element. Now, let's talk about protons, because protons, as it turns out to chemistry, are super important. Number one, they're found in the nucleus, okay? So you'll notice when I draw little Bohr models of the atom, I put my protons in the middle along with my neutrons, okay? Usually for protons, we just put a plus. So this would be helium. We put electrons outside, okay? Notice if I'm doing helium and I have 2 protons, in order for it to be the element helium and for it to be neutral, all right, I have to have 2 electrons as well. They have an approximate mass of 1 AMU, right? An AMU is defined as 1/12 of a carbon-12 atom. It is an older unit that was defined in the 60s, but it is useful for comparing the atomic mass of different elements, okay? This is the big one, right here. Each element has a different number of protons. The protons determines the identity of an element. If you have 6 carbon elements, if you have 6 protons, then you must have carbon. If you have 7 protons, then you must have nitrogen, right? If you have 8 protons, you're talking about oxygen. The proton determines who the element is, okay? Now, when you're looking at an element tile, like this is the tile for carbon, you're going to see the symbol in the middle. They can put the mass top or bottom, but it's always going to be opposite the atomic number. So like on the periodic table that I sent you guys, it has the mass up here and it has the number down here. Either one is fine, right? It can flip. In this tile on the screen here, it's been flipped. It's got the atomic mass number at the top and it's got the average atomic mass at the bottom. Let's talk about neutrons. Neutrons have no charge. They do have mass. Okay, so this is really upper level stuff as far as importance, but the mass of the neutrons lends stability to the nucleus. Okay? And so if you don't have enough neutrons, your nucleus will not be stable. If your nucleus is not stable, it can fall apart, and that's what makes something radioactive. Okay? If you have protons and neutrons with similar masses, or since they have similar masses, we pretty much just round them to 1 AMU. Just a second, they're playing music again. Sorry. Anyway, remember Chadwick discovered the nucleus, okay, or the neutron. Wow. And as long as you know about the mass for right now, that's good. Electrons were discovered by Thomson. The charge on the electron was discovered by Robert Millikan, and they move as both a particle and a wave. Okay. They are found in the electron clouds, and we don't really worry about their mass. So for the conversation we're about to have, you can pretty much forget about electrons when it comes to isotopes, because isotopes talk about mass. Now, what is an isotope? Okay, this is the definition right here that you want to have down pat. It is an element with a different number of neutrons in the nucleus. It does not change the identity, okay? So we'll see on the next slide, carbon 12, carbon 13, and carbon 14. They're all carbon. If you try to define their behavior, they're going to behave like carbon. The problem is neutrons affect stability. So if you don't have the right number of neutrons, you can end up with radioactive, in this case, carbon, which you can have. So in just simplest terms, the number of protons in an isotope between two isotopes are the same, but the number of neutrons is different, so the masses are different. There's two ways we write isotopes. We use hyphen notation, we use nuclear notation. So let's look at hyphen notation. So here are 3 isotopes of carbon. All right, so that's how we would describe this. These are 3 isotopes of carbon. We have carbon 12, carbon 13, and carbon 14. Okay, so you read it. Oh, sorry, wrong thing. Eraser. All right, you just read the word, and then you say the number. And the number is the atomic mass number. All right, now its symbol is A. Okay, so we would say a generic form would be element hyphen A. Remember, Z is the atomic number. A is the atomic mass number. You might be thinking, what is the atomic mass number? That would be a valid question. The atomic mass number, A, equals the number of protons plus the number of neutrons. Pretty simple. You can use that information and the name of the element to figure out how many neutrons are in each of these. Carbon 12 has an atomic mass number of 12. Protons in carbon, when I look up carbon, carbon has 6, plus neutrons. So if I want to know how many neutrons are in carbon 12, I just, right, because this is protons, I just subtract 6. So 6 equals the number of neutrons in carbon 12. Okay? If I want to look at carbon 13, well, now the mass is 13. So 13, it's still carbon. So I look up carbon, it has 6 protons, plus the number of neutrons, still subtract 6. Now 7 equals the number of neutrons in carbon 13. And obviously 14 would have 8 neutrons. Okay, so that's what we use this for. Now, carbon 14 is radioactive. And when they do radiocarbon dating, they use carbon 14. Do that.
All right, they do in 3.
All right, hold on. I got to go cut the music off again because apparently we're playing music over the announcements. Just a second. While I'm doing that, look at nuclear notation. All right, so nuclear notation. Nuclear notation is the one that I prefer. All right? I think this is a better form of notation. But as it turns out, hyphen notation is great for when you're writing papers. Nuclear notation is better when you're doing calculations. We do more calculations than papers in here, so I like nuclear notation. And nuclear notation prevents you from having to look things up on the periodic table. It gives you the symbol of the element, right, which we abbreviate X. All right, so there's the symbol, okay, for element symbol. It's X, capital X. It gives you the atomic number, Z, and it gives you the mass number, A. And so with radium, right, the easy thing about nuclear notation is it's already set up your subtraction problem for you. So we know that the mass number is the number of protons plus neutrons. And so we know if we subtract the protons from both sides, right, A minus P plus equals N0. Another way you could write that would be A minus Z equals neutrons, right, because P plus equals Z, right, equals the atomic number. The protons equal the atomic number, all right? But we don't usually do the Z because it looks like a 2. Anyway, they've already set it up for you. 226 minus 88. So if I want to know how many neutrons there are, I just subtract that and I get 138. Yes, 138. All right, neutrons. So I like nuclear notation better. Plus, we use nuclear notation in nuclear reactions, which we'll get to shortly. So that's the difference in hyphen and nuclear notation. Remember, both of these describe isotopes. All right. So if I just have some generic isotope and I want to write it in nuclear notation, do X, A up top, Z down bottom. Right. And you may have noticed I've done this already when we talked about Rutherford. If you want to go back and look for it, I talked about the alpha particle, right? So let me erase some of this stuff. All right. So I told you that the alpha particle that Rutherford discovered, okay, that he used in the gold foil experiment, I told you it was a helium nucleus, 4,2 He, and that's how I wrote it in that other slideshow, in that other video. And so this is the nuclear notation for an isotope of helium. And we can look at that and we go, oh, okay, well, we know it's got 2 protons and it's got 2 neutrons. Look at that. And I told you it's only the nucleus, right? An alpha particle is a helium nucleus. And so hearing that, you should know, oh, it doesn't have any electrons. So it's actually a positively charged particle because it doesn't have any electrons to get rid of that, right? That positivity. So learning about these things, great. Being able to identify these things, great. But it's also really important that we can apply stuff we know from other lectures as we keep going. Remember, chemistry builds on itself all the time. So learning that electrons are negative and that protons are positive lets us predict behavior about something like an alpha particle when we hear that it's just the nucleus of a helium atom. And that tells you, oh, there's no electrons. If there's no electrons, it must be positive, right? So we want to be able to connect some of those dots. Now let's look a little bit closer at this atomic mass number, okay? It's the number of protons plus neutrons in the nucleus, okay? Please don't forget that the atomic number is the number of protons. And so we've been using this formula in the last 2 slides, but here it is in case you need to write it down. You could also obviously write A equals protons, P plus N0, neutrons, right? These 2 things are the same, right? They are equal to each other. Now you can practice some of these, all right? I'm giving you these guys too. I'm going to do 2 of them with you, all right? One from each side, and then you guys do the rest, okay? Hopefully this will be pretty easy, but I'm going to do uranium-235, and I'm going to do, we'll say, krypton 36, okay? Or excuse me, krypton 84. So for uranium-235, I need to look up uranium on the periodic table. So uranium, the symbol is U, all right? And when I look it up, I find that it's number 92, all right? So it is 92 protons. So I say 235 minus 92 gives me 3. 13 minus 9 is 4. So I have 143 neutrons. So if I wanted to determine the number of each subatomic particle in uranium-235, this is the answer I need to give. P plus equals 92, N0 equals 143. And since it's an element, right, since it's neutral, electrons must equal 92 as well. And that is the answer that I would turn in to answer this question, right? Each subatomic particle means I want protons, neutrons, and electrons, right? Don't just stop here, okay? If you stop there, you get a third of a point. So you read the question and answer the whole thing. All right, let's do krypton at 84. Okay, and you'll notice when I read this, I read it in hyphen notation. I'm just reading the element, krypton, and then the mass number, 84, okay? But in order to work my math problem, I don't have to look anything up, right? All I have to do is subtract. So 14 minus 6 is 8. 7 minus 3 is 4. So 48 is the number of neutrons. So my answer, I would say E minus equals 36. P plus equals 36. Is that right? Check that math. Yeah, 48. And my neutrons equals 48. Okay? And I box that in. That's my answer. Okay? So you guys do the rest of these. Okay? I did uranium and krypton for you. If you have questions, let me know. All right, I'll be glad to help you out. And keep on working. All right, so let me get rid of some of this stuff here. Stop presenting. Okay, so just as some reminders, remember, emails are like raising your hand. Send them often, send them early. If you have a question and you don't reach out, I can't help you, right? I can't read your mind. Make sure you're not leaving things to the end of the week. All right, let's get them done early. As soon as you finish something, just go ahead and turn it in. All right, don't wait till Sunday. That way I can grade it and get it back to you. All right. If you have questions, again, reach out, and I'll see you guys in the next video. All right.